Hello, everybody. Hope you're having a good Monday, and I will definitely be back tomorrow to continue on with you in Chapter 17 with thermochem. But we're going to start today on page 2 of your packet with some of your intro notes to thermochem. So if you turn there, we're going to start filling stuff out. So remember in Chapter 17, if you looked through the packet yesterday and from the intro videos that you saw, we're going to be studying energy changes. And we're looking at energy changes that happen during chemical reactions and between changes of state. And remember, we did a bunch of changes of states and 2 chapters ago with chapter 15 in states of matter. So there's about 7 different ways that we can calculate energy. Okay, so we're going to go through this chapter and we're going to learn about all these different ways in which we can calculate energy changes during chemical reactions or during changes of state. So the first thing we're going to start out with is a definition for energy and how we can describe energy. So what we're going to think about with energy is the ability to do work. Or we can say to produce heat. Okay. And chemistry, no matter what type of chemical reaction we're looking at, we're always going to be thinking about what ability is there for work, or is there the ability to produce heat. Okay, and we like to think of this kind of change in the chemical reaction and being able to quantify that. So when we talk about heat, heat is when you take energy and you transfer it from a warm object to a cooler object. So heat is the energy that transfers from a warmer object to a cooler object. So keep in mind the stuff that you had in physical science with conservation of energy. So remember, we have to show that energy is being conserved, that we didn't create energy or that we just didn't destroy it or it disappeared. That during all of our chemical reactions, we want to keep in mind that energy is being conserved, and it's going to be our job to show that energy and where it's being transferred to. So the first thing we're going to look at here is going to help us with the first law of thermodynamics, okay? It's that idea that energy cannot be created or destroyed. But it does change from one form to another. Okay, so when we think back to that physical science that we've had before and things that we've learned in here before, law of conservation of energy doesn't seem like a difficult task to think about. And there's some other types of energies that you learned and that you wove together with that. And we've used those when we did our States of Matter chapter as well. And when we put together our heating curves, we included types of energy in those. And so those are the energies that we're going to keep working with. So when it asks us what types of energy are there, we're thinking about the two we used a couple chapters ago. We're going to look at potential, and we're going to look at kinetic. So when you think about potential energy, that is where we're going to say this is stored energy. And if you think about where do compounds store energy, where would those be located? You're going to have to go back and think way back in to your favorite chapters, chapters 7 and 8, and we're looking at bonds, and all of the energy is stored in the bonds of these substances. So it says in bonds is where you would find all that potential energy. And then kinetic energy. So this is motion energy of motion. And this goes along with the video you saw yesterday with those nice little cartoon guy and the Eureka videos. And what you're looking at with motion of energy is all about its relationship to temperature. Okay, so kinetic energy, we're looking at the motion, that the particles are moving, and for us, we're relating that to temperature, and that's how we're able to read their ability to move. Potential energy is where we're going to start studying their bonds and how much energy is inside those bonds. So we need some units in order to be able to measure energy, and there's a couple units that we can use, or as you read through chapter 17 and you did some summaries on, that pop up in this chapter. So one unit that we can use, or how energy can be measured, is a calorie. So you have something that's called 1 calorie. Okay, and a calorie is equal to a term that you've had before in physical science, and for the couple of you who are in physics, it'll be much more familiar to you. Or if you continue studying after this and go to physics, this will be an area where you see something that's familiar to you. And that's called a joule. And inside a joule, you would have 4.186 joules is the same thing as a calorie. And so just like we have grams for mass and we have liter for volume, the SI unit for energy is going to be a joule. And the symbol for a joule, if we're going to write it in shorthand, is an uppercase J. So we'll be using that a lot. When you think about calories, and that we have 1 calorie equals 4.186 joules, hopefully what comes to your mind is maybe food you eat, things you drink. They all have calories in them. And so the idea is, in a calorie, what they're trying to describe to you is they're trying to look at the amount of energy. So it's how much. It's the amount of energy needed or required to raise 1 gram of water 1 degree Celsius. Is what we're looking at when we're talking about this word calorie. So just like other units of measurement that we can have something that's in the form of calories or kilocalories. We can convert it and put different prefixes out front. The other option that may pop up or might sound familiar to you in your book is this is 1 calorie with a lowercase c. They also have something called a big calorie. And 1 big calorie is equal to 1,000 little calories. Okay, so when you look at food labels and things you eat, those are identified with big calories. So if we're looking at eating or drinking, say, a can of soda that has 150 big calories in it, okay, really that's 1,500 little calories. So the labels can be deceiving to us here, especially in our country, where our goal is to make those numbers as small as possible on the wrappers, versus some of the other countries who will label their food with units of joules or energy. Miss Waba might have left a few wrappers out to pass around from her travels. So if she has those out and about, they'll be coming around so you can kind of see how things are labeled. If you've been fortunate enough to travel out of the country before, you might have noticed those on labels or read them before. But each country has a way of displaying that nutritional value to you. So that's just another way to think about what we're consuming and how much energy our body is using to burn off those calories. So for us in chemistry, so much it's not necessarily all about our nutrition, but these chemical reactions. So let's look at some of these unit conversions here in your notes. So the first one has you taking 782 joules, okay, the uppercase J, and they want us to convert that to calories. So just like we did any other conversion since way back even in August, you start with what you know. You have 782 joules times slash, and then use the conversions that we have. And every 4.186 joules, there are 1 little calorie. Go ahead and, I don't know, Ben, punch this into your calculator for everybody. You get to keep 3 sig figs, right? So hopefully right now Ben's yelling out to you that you'd have 187 calories. Okay, if we look at the second one, we have 2,000 little calories times slash. For every 1 little calorie, we have 4.186 joules. All right, so if Lane was punching this one in for us, when she's done, she might read her calculator display for you guys, but you should get 8372. If we were following sig figs, however, we would record 1. But for this instance, guess what? I'm going to put a little dot right here at the end of my 2,000 calories, and that way I can keep all 4. For the third one, it says 650 little calories. How many kilojoules do we get? So let's start this one out just like the rest. What we know, 650 calories times slash. What we know is that in 1 little calorie, there's 4.186 joules. And so if we were to stop here, we're at that base unit. We're at joules of energy. That means we've got one more step. We want to leave our base of joules and go to kilojoules. Just like you'd go from grams to kilograms, there are 1,000 base units, 1,000 joules, and 1 kilojoule. So we'll go ahead and we'll punch that in. If we're cognizant of our sig figs, we're going to keep 2 of them. So we're going to keep 2.7 kilojoules. All right, and the very last one over there I'm going to leave for you guys to do on your own. Running out of room on my screen. But you have 0.09 big calories. They want to know how many little calories do you have. So you would start that out. 0.09 big calories times slash. And then remember up at the top we said 1 big calorie is the same thing as 1,000 little calories. So if we get to the end and we want to keep just 1 sig fig, we're going to end up with 90 calories. Okay, so hopefully those seem pretty easy. Those are conversions. We've done lots of metric conversions throughout the year. This is the one that pertains to this topic. Okay, so let's keep going down our list here. The next thing on our sheet says, what is heat, or in parentheses, enthalpy? Those are two words that you're going to see used interchangeably a lot, and they'll switch back and forth between them. But what is heat is we're looking at the flow of energy due to a difference in temperature. Okay, and there's a couple different ways that we can shorthand this, that we can use symbols to represent this heat or this enthalpy. One of those is going to be by the lowercase q, that's almost written in cursive. Okay, so this is a measurement for heat. Okay, you also have something else we'll see, which will be delta H. Looks like an uppercase there. And what we're going to use there is that's going to be our measurement for enthalpy. Okay, so you're going to see Q be a representation for heat. You'll see delta H as a representation for enthalpy. Okay, you can kind of think of delta H and enthalpy as an example for chemical reactions. When you think about heat and Q, we're talking about this process that's happening, like an ice cube that's melting. Try to squeeze that in here. Okay. As some examples to give you that you can think of. We'll see a bunch coming up here when we start practicing with our homework. Okay. So the next thing that confuses people, or that students have a little bit of difficulty with, is describing, well, what's the difference between heat and temperature? Okay, there is a difference between heat and temperature. They're not the same. So if we're looking at temperature, temperature is a measurement. Okay, and it's a measurement of random motion of particles in a substance. Okay, so temperature is a measurement. It's something you read from a thermometer, and what you're reading is these random motion of particles within a substance and how fast or how slow they're moving. Heat, on another hand, is the flow of energy due to a difference in temperature. Okay, so heat, we're looking at this flow of energy. We're going to look at how the energy is being transferred due to these changes or this difference in temperature. So let's use this example to kind of get you to start thinking about it. It says a bucket of water and a cup of water. So you have a bucket full of water and you have a cup full of water. They're at the exact same temperature. It's going to ask us to compare the amount of heat that each contains. Okay, so they're at the same temperature. Okay, and if we know they're at the same temperature, we also know something else about them. We know that they're both at the same average kinetic energy. If they're both at 50 degrees Celsius, then both of those items have molecules moving at the same rate. Okay, which we could also say their speed of the particles are the same. So far everything's the same. We have all these similarities. here's what's different. Okay, what's different is the quantity of heat. Okay, which one has the larger quantity? So in that case, we're going to say that the pail has more energy. Okay, so if we're comparing them, they have lots of things in common. Okay, when we're looking at, well, what's their difference? What's that contrast? Why aren't they exactly the same? If we talk about the quantity that we have, then we know that there's a lot more in our bucket. Therefore, it has way more energy than our cup of water would have. So as we continue to go through this remaining chapter topics, we're going to use kind of perspective when we're discussing things. And based off of the perspective we're looking at, will help us in answering questions. So I want to introduce to you this idea of a system and the surroundings. Okay, so if you want to think about a system versus the surroundings. The system is what we want to study. The surroundings is everything else. Okay. If we want to talk about the whole universe, it's equal to both of those added together, the system plus the surroundings. So if I draw you a little picture here real quick, okay, here's my picture. Okay, my system is this little black circle. Okay, that's my system. Everything around it is the surroundings. So we're going to take on the perspective of, am I on the outside and I'm looking in at the system? Or is it the other way around? I'm inside the system. What's happening in the surroundings? So we're going to use this idea of perspective and where we're at as we move forward, and we're learning about all of these ways to calculate energy. So remember, sometimes it's about your perspective, where you're at in relationship to what we're analyzing. All right, so let's go ahead and flip it to the next page, or page 3 in your packet. All right, here we go. At the top it says exothermic and endothermic reactions. Okay, remember things that are exothermic, that exo prefix tells you things are moving out. Okay, and remember thermic is representing heat, so we're looking at outward heat. Okay, and with endothermic, you've got in. Okay, thermic is still heat, so we're looking at reactions where heat is into the system versus exothermic, where we have heat leaving our system. So if we use that diagram that we just drew a second ago and give that same kind of representation, here's our box. Here's our system. If we're looking at things that are exothermic, we have heat that's leaving the system and going to the surroundings. Okay. And an endothermic reaction, here's our little system, we would have heat coming into the system. It's leaving the surroundings and coming into the system. Okay, another way we've mentioned this is heat's absorbed versus heat being released. Okay, and so for the rest of our notes today, we're going to use these two terms and kind of graph their definition, so to speak. So here's your definition for exothermic reactions. Reactions where thermal energy or heat is given off. So let's write an equation that has an example. All right, so we have 14 KMNO4s. KMNO4 is one of our reactants. And to that we have 4 C3 H5 parentheses OH3. Those are going to be our 2 reactants. And then the products of our reaction are going to be 7 potassium carbonates, K2CO3, and you're going to have manganese oxide, and we're going to have 7 of them, Mn2O3, and 5 CO2s, and 16 waters, and energy. All right, lots of big compounds there. What if we wanted to just simplify it a little bit and use letters from the alphabet? We'd have something like A plus B gave us C plus D plus some more plus energy. Okay, it's kind of the real generic form, right? But we have our actual example there. And so let's diagram this out a little bit. So we're going to draw a y-axis here and an x-axis. Let's label our axis. So y is going to be energy, uppercase E. Okay, along the x is the reaction's progress. So what we're going to look at is this idea that we're giving off heat. So our reactants are going to start up here. Okay, and by the time we finish, our products are down here. So if we draw a graph for this, we get something with this curve that looks like that. Okay, so if we label this out where we're starting, this is our reactants. You could also write on that line there 14 KMNO4 plus 4 C3H5 OH3. Those are your reactants. Okay, and way down here at the bottom are our products. And you could write those out longhand if you wanted to as well. Okay, but what we're going to look at is we have this hill, this hump up here at the top. Okay, and in order for our reaction to go and for us to get these products, we need something called activation energy, or what we have is big E, uppercase E with a subscript A. Okay, and that's activation energy. And every reaction has it. It needs energy to get started. So once we get over this hump and we've activated our reaction, then we can start forming products. Okay, and when we look at heat and what happens to the heat, what we're looking at is what's the difference? What's the change that's taking place? What is delta H? What is the enthalpy for this reaction? Okay, and how we find delta H is we take the delta H is equal to the heat of the products minus the heat of the reactants. And when we do that, we're going to find out that delta H is always negative. For these exothermic reactions. Okay, you're taking something down at the bottom here and you're subtracting it from this larger quantity of energy you have in the reactants. So you're always going to come up with a delta H that's negative when we're thinking about exothermic reactions. Okay. So in order to help you think about why that happens is there's some potential energy in our reactants that was released to our surroundings. Okay, so all the products have a lower potential energy than the reactants do. And so we're going to get a delta H that's always negative. Okay. All right. So let's look down here at endothermic reactions. We have reactions where the thermal energy or the heat is being absorbed. So just like before, let's do an equation here. So let's do barium hydroxide plus 2NH4Cl yields barium chloride, 2NH3, and water. Okay, and this time there's going to be energy also on the reactant side. These two solids that we have, this barium hydroxide and this ammonia chloride, can't collide. Okay, so in that product side, I'm sorry, I said that wrong, didn't I? Let me rewind that here for a second. And we're looking at these two solids, the barium chloride and this ammonia that we have. They can't collide, they can't interact. So we have water over there as a way to allow them to move around. Okay, so this is something that if we were touching it would feel cold. Okay, so let's graph this and see what similarities do we notice between exothermic and endothermic and what things are different. Okay, so just like before, you're going to label your x and your y-axis. They're going to be exactly the same. Okay, we've got energy on the y. You've got reaction progress on the x. Okay, this time our reactants are down here to start. Okay, so here's our reactants. And when we finish, we're going to finish up here with our products. Okay, so our graph's going to kind of go like that. So some things they have in common. They still have activation energy. We still have energy that's required to get up that hill, to get the reaction to start producing products. Okay, and delta H is still found the same way. Delta H, okay, is found from taking the heat of the products and subtracting the heat of the reactants. So in this case, if you have this larger number of energy in your products compared to the reactants, we're going to find that delta H for endothermic reactions is a positive number. Okay. Energy was being absorbed from the surroundings, so our products have a higher potential energy than our reactants do. Okay, so the last thing I want to leave you with is to go back to these simple terms again. Something that's endothermic. Okay, endothermic absorbs heat from the surroundings. It's going to feel cold. Things that are exothermic. The system releases energy from surroundings. Feels hot. Okay. So think about, if I touch these, what do I notice? So in reactions that are endothermic, like when we said in a previous chapter, explain why the process of evaporation is an endothermic process. As it absorbs heat from the surroundings and it pulls away from your body, you touch your body, it feels cold. if the system is releasing energy, it's taking energy and pumping it out, when you go to touch those surroundings, it feels hot. Okay, so it's all about your perspective between that system and the surroundings. Okay, so keep those in mind as you start to go through and do your homework tonight. Okay, so when you go through to calculate some of these, you have worksheet 1 in your packet, back on page 12 to do for homework tonight. The first couple at the top are going to be conversions like we did in the notes, where I want to go from calories to joules or big calories to little calories. You're going to have 2 problems in the center that ask you to describe things, some vocabulary and explaining some terms. And then the remaining are going to have you looking at diagrams of these reactions, looking at a diagram for endothermic and exothermic reactions, and being able to label those, being able to redraw these diagrams and kind of explain their parts. So I'm going to stop right here. If there's any time remaining in the period, you can go ahead and start on worksheet 1. The bell's about to ring, then worksheet 1's homework, and I will see you back here tomorrow on Tuesday. Have a good day, guys.